This lesson's on related rates. Related rates is one of the big topics in calculus, so we'll probably spend a little time here in class and try to get a strong handle on this one. We'll start with this example. We're given the fact that air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. The question, how fast is the radius of the balloon increasing when the diameter is 50 centimeters? We are given that there's the rate of increase of the volume of air in the balloon is 100 cubic centimeters per second. So that's one rate that we're given. And then we're asked a related rate question. They want to know the rate of increase of the radius when the diameter is 50 centimeters. It's important to note and understand that rates of change are just derivatives, or derivatives are rates of change. So we could say that we were given dV over dt. In other words, the change in volume with respect to time is 100 cubic centimeters per second. And we're asked to find dr dt, how fast is the radius changing with respect to time, and they're giving us the instant when r is 25 centimeters. In order to solve this problem, we're going to need some kind of function to work on. Since we're working with the volume of a sphere, that would make sense to work with that function. If you remember your geometry, if you happen to be able to look that up online or in a book somewhere, you'd find that the volume of a sphere is equal to 4/3 pi times the cube of the radius, or 4/3 pi r cubed. In order to find dV dt, we're going to have to find the derivative of the volume. So let's go ahead and take the derivative of both sides of this function. The derivative of v would just be 1 times the derivative of v, dV dt, equals the derivative of this right side. The only variable we have here is r, which is good because we're trying to find dr dt anyway. So when we take the derivative of this, we're going to follow the power rule. The 3 is going to multiply by the 4/3, giving us just 4. The 3 is going to get reduced in power by 1 to become a 2. And then we're going to have to multiply by the chain because r is some function of t that we don't necessarily have explicitly defined yet. So that would give us the dr dt that we're going to be needing here. So again, the derivative of the right side, 4 pi r squared, times the derivative of r, which is dr dt. Let's take this to the next slide so we have a little room to work. Our given was dV dt is 100 cubic centimeters per second. We're trying to find dr dt when r is 25. Well, dr dt is here, and we just need to isolate it and get rid of any other variables, replace anything we can. dV dt we know is 100, so let's go ahead and do that now. And let's go ahead and isolate dr dt. We can divide both sides by the 4 pi r squared and reduce. So dr dt is equal to 25 over pi r squared. We need to replace that r with the 25 and then simplify. So we get 1 over 25 pi centimeters per second is the rate. That's about 0.013 centimeters per second. So that doesn't seem very fast that the radius is increasing there. Go ahead and pause the video here if you need more time to digest this or write it down. If not, we're moving on to the next example. In this example, we have a ladder that's 10 feet long resting against a vertical wall. We're told the bottom of the ladder slides away from the wall at a rate of 1 foot per second, or 1 foot per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Well, again, this we see some related rate things going on. A diagram would help a lot. Here's my 10-foot ladder. My wall is a vertical distance, so I'm going to go ahead and call that y. The distance the base of the ladder is from the wall is a horizontal distance. I'm going to go ahead and call that x. And then I'm going to try to determine what they've given me and what they're asking for. They're telling me that the ladder slides away from the wall at 1 foot per second. Well, that's a change in this distance on my diagram here that I'm calling x. So they're giving me dx dt is 1 foot per second. And then they're asking how fast the ladder is sliding down the wall, that would be a change in y. So what I don't know is dy dt, and then at the instant when x is 6, that's the time they're interested in. So let's see, I need some equation that equates all these things. Well, I know if I've got a wall and a floor, if they're built correctly, they should be perpendicular. So it helps that I'm dealing with a right triangle. Once I realize that I'm dealing with a right triangle, I can go ahead and use some Pythagoras. So I know x squared plus y squared equals 100. Again, let's go to the next slide where we have room to work. I need to find dy dt, so that involves taking a derivative. If I take the derivative of both sides, I'm going to start with this x squared. The derivative of x squared is 2x, but I need to multiply by dx dt to follow the chain because we're doing this with respect to t, and x represents some function of t. Same thing with y squared. I'm going to have 2y dy dt, and then equals. The nice thing about constants is when we take the derivative, they just go to 0. So that simplifies the numbers anyway. We don't have any large numbers anymore. Let's see what we can replace. dx dt is 1, so we'll be able to put that in. And we're interested in when x is 6, we'll be able to put that in at some point here. Let's see, 2x times 1 is 2x. If I subtract that to the other side, I get 2y dy dt equals negative 2x. I'm trying to isolate dy dt, so let's go ahead and divide by the 2y. And again, at this point, the 2's will reduce out, so I get dy dt equals negative x over y. I know that x is 6 because that's the time they told me they were interested in, or at the instant when x was 6. But they didn't tell me about y. If I go to my diagram here, or my function here, though, when x is 6, I should be able to determine y. When x is 6, I have 36, so y squared is equal to 100 minus 36, which would be 64. Therefore, y would have to be 8. We only need the positive value here because we know that we're looking for distances. So we just noted that when x is 6, y has to be 8. Therefore, when I substitute 6 and 8 into this function, I know dy dt is negative 6/8, which we should always reduce to 3/4. So how fast is that ladder sliding down the wall? It's sliding down the wall at 3/4 foot per second. Okay, again, if you need to pause here, go ahead and pause and digest this a little bit. Otherwise, we're moving right on to the U-try. In this U-try, this is a little different because you're not given any values. You're just given V is the volume of a cube with edge length x, and the cube expanding as time passes. You're just supposed to find dv dt in terms of dx dt. So we don't have any values to substitute, so it's basically kind of the setup of the problem and then stop. Go ahead and pause the video right now and then try this problem. And when you're ready to check your answer with mine, press play again. Okay, all I did on this one was I know that v is equal to x cubed, and I'm looking for dv dt, so I went ahead and took the derivative of both sides. So the derivative of v is dv dt. The derivative of x cubed should be 3x squared times dx dt. I have to follow the chain. And then I'm done, because all they asked for was dv dt in terms of dx dt. And that's what we have. dv dt equals 3x squared dx dt. Okay, on this next U-try, we're given the fact that each side of a square is increasing at a rate of 6 centimeters per second. The question, at what rate is the area of the square increasing when the area of the square is 16 square centimeters? Let's go ahead and pause the video, give this a try. When you're ready to check your answer with mine, press play. Okay, let's see how we did here. Each side of a square is increasing at a rate of 6 centimeters per second, so that's a given rate. At what rate is the area of the square increasing when the area of the square is 16 square centimeters? So if I call the length of the side of my square x, I can say that dx dt is 6 centimeters per second. You might have chosen a different variable here, and that would be okay. And what is the area of the square? Well, I would call that a. So they're asking me for dA dt. What is that when the actual area is 16 square centimeters? my function area equals side times side, or in my case, x squared. If I take the derivative of both sides, dA dt equals 2x times dx dt. I need to know x at the instant the area is 16. I think a little bit of thought will tell us that x would have to be 4 for the area to be 16. It'd be a 4 by 4 square, or a square with 4 on each side. Dx dt is still 6, so we can make those substitutions and find out that that rate is 48 square centimeters per second, is how fast the area is increasing at that instant in time. If you need to pause here for a minute, that's okay. Otherwise, we've reached our learning target and we're ready to move on to the next thing.